Thank you very much. So this is a problem which is basically trying to understand a little bit about what happens when you form sea ice. And this initial simulation here is a little bit misleading because that's not really what I'm going to talk about, but it looks quite nice. So sea ice is a mushy layer, and a mushy layer, for those who aren't familiar, is basically a solid matrix bathed in some fluid. The fluid has two components, one of which will solidify to form the solid matrix. So for sea ice, as you can see in this MRI scan here, you've got fluid which is salt and fresh water, and the fresh water will solidify out to form the ice. Your solid matrix will impose some permeability on the system which will control fluid flow, but conversely the transport of salt and heat can change the solid matrix via dissolution, solidification and melting, so you get some interesting nonlinear and coupled effects. In particular, we're interested in what happens when you start to freeze a salt solution from above, as happens in the polar oceans. Despite the fact we're melting quite a lot of it, we're still forming it in the winter, luckily, so I've still got a PhD project. It also happens in this lab here in Belgium, where they've conducted an experiment in a hilly shore cell, which you've heard a lot about this morning. When you form this ice from above, you create some very dense, salty liquid within the ice, which will tend to sink. As it does so, it will dissolve as it comes down. This will then channel the flow into some very narrow regions, which you can't really see in the ice up here, but you can see where these salty plumes are ejected from the ice into the liquid underneath. And this forms an important buoyancy forcing on the oceans. Conversely, if you're forming a metal from a binary alloy, you want to avoid forming these channels because there will be defects that might lead to weakness. We're going to look at this using a continuum model, so we're going to average over all these complicated fine-scale features to obtain the liquid fraction or porosity, and then we can write down a set of continuous conservation equations. Crucially, we're considering a model for a system trapped in a Healy shore cell, which means that even when you have liquid, the spacing of the plates will enforce a permeability on the system, which is this pi, which means that you can use Darcy's law everywhere, even in the liquid. And just in contrast to some of the Darcy's laws we've seen before, you've got some buoyancy forcing here characterized by a mushy Rayleigh number, Rm, which is a bit like a fluid Rayleigh number, but also includes the effects of permeability and is typically of order 10 to 100. The bulk salinity will evolve due to the advection and diffusion of the liquid phase, and the heat or enthalpy will evolve due to advection and diffusion of the temperature. The temperature, liquid salinity and porosity are in turn calculated from the enthalpy and the bulk salinity according to some phase diagram that we'll prescribe. And we assume that there's this idea of local thermodynamic equilibrium, which means that wherever you have porosity less than 1, so you're in the mushy layer, the temperature is tied to a liquidus, which is controlled by the salinity. What this basically means is that as you get colder, you also get saltier. These are the dimensions of parameters you end up with in order of more interesting to least interesting, and it is really just the Rayleigh number that we're interested here. There's a Lewis number which controls salt diffusivity, and a Stefan number which describes how much your latent heat is. You can solve those equations, and we've done it here for a 2D salty box which is freezing from above. I've plotted the porosity, wherever it's less than 1, that's this white icy stuff at the top, and then in the liquid phase, I'm plotting the salinity, so you can see these really salty channels leaving the ice. These are all the gory details. I'm not going to talk any more about that. If you want to, you can find me afterwards. And what you find is some really interesting nonlinear effects. So firstly, you can see initially you have quite a tight channel spacing, and then over time the spacing coarsens. And you'll see a transition from these straight channels to wavy oscillatory channels. It's all really interesting, but it's a bit complicated. So I'm not going to talk any more about that either. I'm going to construct a slightly simpler environment to study these systems. The first thing I'm going to do is infix a growth rate. So I take my Healy shore cell, it's this thing here. In particular, I'm interested in the region D, and I'll fix it between two heat exchangers, B. This is an experiment. I'm doing numerics, but this is what it looks like in the lab. And you translate your Healy shore cell at a fixed rate between these two heat exchangers, V frame, and that enforces a growth rate, enables you to find steady-state solutions that look a bit like this. We then wish to take advantage of the periodic nature of these systems to simply solve in a box that's this big rather than this big because it's quicker. To do that, you need to have some idea about what the spacing is between these channels. And we'll assume this thing called the optimal flux hypothesis, which states that the channel spacing left to its own devices will adjust to maximize the flux of salt through the channels. What this means practically is that if you take your box that's this big, you vary the length of your box and you keep solving your equations, you measure the flux and you get a curve like this, you take the solution that's up here. Doing this, you're then able to span a wide range of parameter space, and I've plotted a few example steady-state solutions here. You see a region of solid ice at the top of the domain, a mushy layer with this porosity in the middle, and then the liquid at the bottom, and I've truncated the bottom of my computational domain. We're interested, as I said, in the variation of this Rayleigh number, which characterizes the effects of buoyancy, and also the concentration ratio, which says a bit about how salty your fluid is. Essentially, the saltier your fluid is, so that's the bottom one is more salty than the top one, you have more porous ice because you don't freeze as much. As you increase the Rayleigh number, you increase the strength of your flow and you reject more salt, so moving left to right, you increase Rayleigh number, and now you find that your porosity has decreased again. So this is qualitatively what happens. What we're really interested in, from a geophysical perspective, is what this salt flux is. So we've measured it. I've plotted it on two separate figures here because as you vary this concentration ratio, which said is basically describing the salinity, you get a wide range in the salt flux. So the scale on the right for the smaller C is much smaller than the scale on the left. Firstly, draw attention to these high concentration ratio regimes here where the salt flux scale is linear with the Rayleigh number. This has already been explained and observed. What's new is this low concentration ratio regime over here, where you have some sort of sublinear growth, and we'd like to explain that. You can see that the salt flux, if you integrate it across the bottom of this channel, will probably scale something a bit like this, where you've got a stream function in the channel, and then you're interested in the flux per unit length convection cell. And we're going to build up very quickly a scaling argument for what this salt flux might be. So rewriting Darcy's law as a vorticity equation, writing out my steady state conservation equations where I've added this frame translation velocity here, which accounts for the fact that we've put our thing in a translating Healy-Shore cell. We can first look at these channels, which we'll consider to be narrow relative to their height. The flow is driven by buoyancy forces, whilst the advection of salt is balanced by horizontal diffusion of salt, which gives us a scale for the stream function there. The height of these mushy layers is determined almost exclusively by diffusive effects, so balance of diffusion and latent heat release. It doesn't really care about the flow. The flow actually is really constrained to a high porosity region at the bottom of the ice. If you plot the diffusive solution, that's the temperature and the permeability in these curves here, you find that the diffusive solution to this problem sets up this high permeability region, and the flow is really not able to penetrate much further below that. The salinity is basically going to also obey this diffusive solution, so it's going to vary roughly linearly of height, giving us a scale for the salinity at this region at the bottom, and we can again write down a momentum balance. The flow that this generates is going to penetrate a bit further into the ice. It's going to be characterized by the height of these channels, so we can write out sort of a residual temperature balance, where you've got diffusion on the right here balancing advection. And then finally, there's one more ingredient I need, which is something I can't justify a priori. If anyone can see where this comes from, I'd be very grateful, but I can't. We see it in our numerics. But we stick this in, we put it all together, and we find a scale for our convection cell width, which scales like, well, quite weakly, 1 over Rayleigh number to the quarter. Then there's a Stefan number to the half, and this is our fixed growth rate to the half. You put these components together, see what the salt flux is going to be that we predict, and then see does this agree with our numerics. So the scaling for the stream function in the channel and for the width of the convection cells collapses our data quite nicely. For the salt flux, the collapse isn't quite so great, but as you go towards this very small concentration ratio regime where I expect our results to hold, it's a little bit better. It breaks down basically as you get too salty and the flow can penetrate up to the top of the mushy layer. Very briefly, because I'm into injury time, we find, just to think about some of the physics after having done this maths, the concentration ratio here, this is dependent basically because as you increase the saltiness, you increase the buoyancy forcing and you increase the mass flux through the channel. As you increase the buoyancy forcing, you both increase the mass flux in the channel, but also make your channels closer together. And as you increase your growth rate, you make your channels closer together, which again increases your mass flux per unit length. I'll leave you the conclusions.
Thank you very much. Good question before our next speaker gets going. I've just got a question myself. I mean, you've got this optimum flux condition, yeah?
Yeah.
During numerical simulations actually support that? I mean, you've done
So
yeah.
to test that, you need to run simulations in as wide a domain as possible.
Right.
And they haven't finished running yet.
Ah, okay.
There's
We'll know the answer in due course.
some experimental evidence that suggests this might be true.
Okay, thank you very much.
Thanks, Chris. So most of you in this room will probably be thinking, what on earth is an F layer? More specifically, what in earth is an F layer? So in order to explain what this is, I have to sort of give you a brief overview of what's happening inside of the Earth's core. So what is it doing? It's vigorously convecting because it's chucking out a ton of heat. So it's all convecting and it's very well mixed. The core is known to be composed of an iron-oxygen alloy. And this is useful because it induces an electromagnetic field and it generates this is powered by a dynamo process. And the energy sources that power the dynamo are predominantly secular cooling, which is the heat lost over time. You get latent heat release because phase change at the inner core boundary will release latent heat. And also you get a load of power from gravitational energy because light elements will differentiate into the liquid outer core. And this buoyancy will stir up the dynamo. So the F layer is based at the bottom of the outer core. And basically, because we know that the core is predominantly well mixed, it will approximate an adiabatic profile. So the density should correspond to that traditionally. But there's been some recent seismic observations that there is this F layer which is stably stratified. So the observations are inferred by slower than expected P wave velocities. And this means that the F layer has to be we can infer that it's stably stratified. So the key question that my project addresses is, how can the light elements that are being differentiated into the liquid outer core pass through a stable layer without disturbing the stratification? So initially you might think that the layer could be explained by a simple thermal boundary layer where you have cooler stuff overlying hotter stuff. And so perhaps that would mean that you have lighter material at the bottom. But this will give you the wrong kind of density profile because it will be, the density will be increasing as a function of radius, when in actual fact you want a stably stratified layer in which the density is decreasing as a function of radius. So moving on to the next sort of model up, perhaps there's a chemical aspect to explaining the F layer, in which you have more light material at the top of the layer overlying heavier iron. But this kind of system doesn't really address the expulsion of light material directly at the inner core boundary. So this stable stratification is just going to be mixed up anyway. So in my project, what I've done is sort of move to the next level up and introduce solid phase into the system. So rather than light material being expelled into the liquid directly at the inner core boundary, it happens everywhere throughout the layer. So solid material is crystallizing from the ambient fluid everywhere, and it sort of snows down towards the inner core to grow it. And this allows light element to be transported through the stable layer, which would be nice to explain the geophysical observations that I mentioned earlier. So in order to formulate the slurry problem, it's quite a complicated system. So I've had to make use of two approximations, the first of which is fast melting. So if you consider an infinitesimal volume of fluid, it will either contain solid phase or liquid phase, and there's nothing in between. So because we have this phase equilibrium between the two phases, the temperature will always follow the liquidus within the F layer. And as I mentioned earlier, the outer core will be following a adiabatic temperature profile. The second approximation that I'm going to make use of is that I'm going to assume that the core is composed of a binary alloy, because in reality there's a lot of other junk in the core. But to reduce possibly a two-phase, two-component system, I can use the fact that other calculations ab initio calculations have shown that oxygen will partition entirely into the liquid phase. So I won't get light element in the solid phase. So this reduces the degree of freedom of the system from a two-phase, two-component mess. So here are the governing equations for a slurry. And the first one is the most important one because this is the liquidus relation is a consequence of the fast melting approximation. So it just tells you how the temperature is being depressed by the presence of light element, and also how it changes because of the effective pressure. The next equation is the temperature equation that we all know and love, but it's augmented by a latent heat release term because of the solid phase being created in the layer. I've got a conservation equation for the oxygen in the layer and its associated flux, and another conservation equation for the solid mass within the layer. But this is not conserved because there's a source term in which solid phase can be created in the layer and its associated flux. And then we're working in a Boussinesq framework, so here are the equations of mass conservation and general momentum equation. So it's quite a complicated system, the details of which are sort of covered in a paper that came out earlier this year. So here's a shameless plug of my paper, go read it. And also in this paper, I look at the steady state problem and find some solutions to that. But today I don't want to talk to you about a steady state problem. I'm looking at a more interesting time-dependent model. So I basically treat the slurry as a Stefan problem, which is a class of boundary value problems that deal with phase transition and the associated moving boundaries. I'm also idealizing this system as one-dimensional in radius. I've also assumed that we have a static slurry, so there's no flow velocity in there. Another assumption is I'm assuming that the inner core is isothermal. In reality, it's somewhere between isothermal and adiabatic. So in order to augment for that, I've introduced a small sort of interfacial freezing term at the inner core boundary so that you don't get boring constant solution temperature profiles, and it lifts the temperature from the inner core onto the liquidus. As I mentioned earlier, the outer core will follow an adiabatic profile, and the system is solved subject to 6 boundary conditions. So you've got the continuity of heat flux at both boundaries. At the upper interface, I have a variable concentration of light element. I've also ensured continuity of the temperature at the upper boundary, and I'm imposing a solid flux of 0 at the top. And the parameters that I can adjust with this model are the amount of heat that's being lost from the entire core and the amount of sort of interfacial freezing that I have at this inner core boundary. Also, the speed of the lower boundary is determined by that freezing speed plus the snow speed of the iron particles growing the inner core. So here are some new results that I've only recently obtained, and my supervisor hasn't really seen them yet, who's the chair of this session. So you might be interested to know what they are. It's basically a video of how the temperature profile and oxygen profile is evolving over time, as well as the solid flux on the right. So this is simulated over a time period of 1 billion years. So looking at very long time scales. And if I just play the video for you again, you can see how the layer thickness is going through an initial growth phase. And then at the very end, at about 800 million years, it starts to shrink slightly again. And you can see how the temperature was cooling over time as the core was cooling. And the oxygen concentration at the top is going to increase because of the reduction in volume of the outer core over time. Proceeds. And then here is just how a breakdown of the heat flow, the global heat balance within the core. So I've fixed it at 13 terawatts, the amount of flow, like heat that's being extracted by the mantle. And then if you just look at the secular cooling, which is denoted by the yellow line, you can see that it's extracting a lot of heat from the slurry initially, which makes the slurry snow harder, and you get a lot of layer growth. And then eventually, because the liquid outer core is shrinking in volume, the effect of this decreases over time, which might be related to how you see the layer shrink later on. So this is just a summary of what I've just gone through. Thank you for listening.
Okay, any questions for Jenny?
I'm sure you do.
Is the layer going to shrink away to zero eventually, do you think, or will it...
Will it sort of kickstart again and grow? I haven't seen any solutions like that so far. Quite a lot of the solutions I've found thus far, even though it's only been this week, I've seen the layer shrink most of the time. But if I play with parameters such as the heat flux or this interfacial freezing, then hopefully I can find some more interesting solutions.
If you wait for 1 billion years, the problem will eventually go away.
Yeah.
Right, thank you, Jenny.
Thanks.
Right. I'm going to provide a slight break from the theme of the session because I'm not going to talk about geophysical problems. Instead, I'm going to talk about fusion plasma. And in particular, we're looking at magnetic confinement fusion, whereby magnetic field is used to confine hot plasma fuel to circulate around the toroidal chamber of a tokamak. And perfect confinement would be achieved if plasma particles stayed on the magnetic field lines indefinitely. But in reality, gradients of magnetic field and curvature cause plasma to slowly drift out radially towards the walls of the chamber. And if you look inside at the Perolder cross-section, there are two distinct regions of plasma inside the tokamak. There's a core region that's where the fusion reactions are supposed to take place and where magnetic field lines loop around and close on themselves. So that's a periodic direction. And there's a scrape-off layer where magnetic field lines end on material surfaces. And the idea is that anything that drifts out of the core plasma gets transported along the magnetic field lines and deposited onto target plates before it gets a chance to hit the wall. But in reality, it's been observed experimentally in this picture here that transport in the scrape-off layer is dominated by these intermittent ejections of dense blobs of plasma that propagate all the way to the wall. And so in this talk, we're going to address the linear stability problem in this region where these filaments are observed to gain some insight in the kind of instabilities that are present. And the simplest models, or we're going to consider a two-dimensional model, and the simplest models consist of evolution equations for plasma vorticity, which is related to potential, and the number density, so that's a density conservation equation. And all the effects of curvature and field gradients are contained within the effective gravitational terms. And this parallel direction, dynamics in the parallel direction is represented through these parallel closure terms, which are basically provide some damping. And what I'm going to propose is that this problem can be thought of as a modified thermal convection problem, where by this analogy, the plasma potential corresponds to fluid stream function, and so on for vorticity, and the logarithm of number density will correspond to our fluid temperature. And if you look back at this picture, let's say x is pointing to the right, my gravity is in the negative x, so it's sideways, and this is my dense, meaning hot, and my less dense, meaning cold. So my convection is rotated 90 degrees. So if we treat it as a convection problem, first thing we do is construct a basic state, and in terms of the number density, the basic state satisfies the linear conductive profile. But I said that analogy is between log of density and the temperature, so we will have to transform that equation. So basic state log density will be logarithmic profile. And if I perturb my equations around this basic state, scale appropriately and linearize, I'll arrive at the following dimensionless equations. And these really do look like a modified convection problem where these modifications are highlighted. And they can be categorized as, firstly, the non-uniform basic state gradient that takes this kind of form. There are linear damping terms, which are representative of these parallel losses. And there are additional two advective terms in the temperature equation. And you can also identify analogs for Rayleigh and the Prandtl number, but note that the Rayleigh number doesn't contain this factor that would describe the density or the temperature difference across the layer. So it really just measures the strength of gravity against the viscous dissipation rather than full buoyancy. So what do I have? Speaking of parameters, okay. There is great uncertainty in really estimating the diffusion parameters, and this breeds uncertainty in my dimensionless parameters, as summarized in this table. So we're going to focus on the effect of variation of the Rayleigh number and the Prandtl number because the uncertainty in those is the greatest. And we follow standard approach. We postulate normal mode solutions, form an eigenvalue problem for the growth rate and the radial structure of the solution, and address the problem of marginal stability. So we're going to seek the minimal density difference across the layer at which the instability kicks in. But at the same time, to gain some analytical insight, because this eigenvalue problem we have to treat numerically because there's an explicit dependence of the coefficients on the x direction. But to gain analytical insight, we're going to formulate a simpler problem. And we do that by noting first that these boundary conditions are formally equivalent to stress-free fixed temperature boundary conditions of the convection problem. And this is the idealized case where solutions to the convection problem take the simple sinusoidal form, and you can write down the analytic expression for the stability threshold. So we're going to formulate a reduced problem by extending the Rayleigh-Bernard problem as far as we can, but still retain the simplicity of its solution. And to do that, we replace this basic state gradient, non-uniform basic state gradient, by just the absolute difference between our boundaries, and we neglect this term completely because it just gets in the way. So then, substituting the appropriate ansatz, sinusoidal, lacking convection, we can write down the marginal stability threshold. And now we can solve the full problem numerically, and we can compare the solutions to the analytical solution of the reduced problem. And this is what I do here. So on the left, I have the variation of the critical density difference with Rayleigh number. So above the curves, I'm unstable. Below the curve, I'm stable. And first thing I want to point out is, as you increase Rayleigh number initially, that has the effect of reducing the density difference. So it means your system initially is going to be more and more unstable, less of a density difference for the instability to sit in, but to the point after which further increase will lead to a stabilization kind of effect. And this is quite unlike convection, where increasing that gravity would mean that I need less of a temperature difference for the instability to set in. So and this behavior is basically because my Rayleigh number pops up in two equations in the plasma problem. It pops up in the vorticity equation, where this is the interchange drive term, which is the direct analog of the buoyancy drive in convection, and this term is known to be destabilizing. It's what's responsible for the instability in convection. But at the same time, I have another term that includes Rayleigh number in the log density equation, and this, in fact, this term has a stabilizing effect, and at high enough Rayleigh number, it's going to compete with the destabilizing effect of the buoyancy drive, hence the shape of these curves. Very quickly, clearly the threshold is Prandtl number dependent. Another thing that's the difference with convection, or at least idealized 2D convection. And overall, there is very good agreement between the results from the reduced system and the full system, full numerical solution. And this agreement is particularly good when we're below 1 on this y-axis here. And that's because, well, my density difference at onset is small, so all the terms that I had neglected in creating the reduced system are small. And in fact, the solution to the full system looks like a sinusoidal solutions to the reduced system. So hence the good agreement. But beyond that, we can see that in the limits of very large or very small Rayleigh number, density difference at onset grows indefinitely. So that means my inhomogeneity of my basic state will be more prominent. And in fact, when delta n goes very large, approaching infinity, my basic state will develop an asymptote around one of the boundaries x equals 1. And that's going to cause the solutions of the full problem to be spatially localized near the x equals 1 boundary and develop sharp gradients characteristic of a boundary layer problem. And this is a summary, and I'm right on time. Thank you for listening.
Any questions for Friedrich? Just one point. Is it going to be possible, do you think, to actually do any nonlinear work on this system eventually? I mean, it's more complicated.
It is the hope of my supervisors, yes. But like you see, the values are extreme of Rayleigh number, and so that's going to be very challenging indeed. Maybe we'll
possibly for more modest Rayleigh.
Maybe, yes.
To see how lots of transport results. Okay, thank you very much.
Thank you, Chris. Right. So, quickly to start, I'll introduce what a gravity current is for those of you that don't know. So, gravity currents are flows that are driven by a density difference. This density difference could be caused by suspended sediment, composition of dissolved material, temperature, or the fluids may be distinct. They occur in many sort of geophysical and industrial settings of great importance, for example, pyroclastic flows, landslides, and glaciers. Now, pulses are an inherent feature in gravity currents, and they can form from the variable supply in material causing instability, or they could be from the combining of separate flows. So, a really nice example of this was the eruption of the Soufriere Hills volcano in Montserrat in the late 1990s. This here, so these pyroclastic flows on the side. The eruption lasted about 25 minutes, but there was 3 distinct pulses during that eruption. And these pulses can transfer energy and material towards the head of the front, and they can affect the internal structure. So the first sort of approach to exploring these pulse flows, I used a experimental modeling with a lock exchange problem. So classic lock exchange problem, you have a big long flume, fill it with an ambient liquid, in this case water, and you have a lock gate with a dense fluid. We used water and glycerol mixture here. At the start of the experiment, you lift up the front gate and the red fluid will flow out, just like a gravity current, and then you observe what happens. So what we've done is we've added another lock gate here, dye it a separate colour, but it's exactly the same as in the red liquid. And at a set time, we release that as well. This creates a pulse which travels through towards the front of the current, and then we film it with either a pair of rolling cameras or a high-speed camera. Yep, so we vary the glycerol concentration to vary the Reynolds number of the flow between 100 and 400. We vary the number of releases between 1 and 2. And we vary the gate separation time in terms of the remaining fraction of red liquid in the first lock gate when we release the second lock gate. So now I'm going to show you a quick video shot with a high-speed camera. This is in quarter speed, so the real event will be going about 4 times as fast as this. So here's the red current coming through as a normal gravity current. And then at some point later, you better see the blue current coming through, which will... Yeah, so here we go. So here's the pulse travelling through. And what's really interesting here is at the start we can see it's mostly in the blue current, but towards the end of the frame here, it's completely transitioned into the red current, and that will go through towards the head of the flow. So most of this talk is going to be about numerical modelling, because that's what I've been doing most recently. We use the depth average shallow water equations. Now these assume that there are no vertical variations and they're inviscid, and also we neglect the flow in the ambient. But really the first 2 assumptions are not really valid near the head of the flow, where you can get significant vertical gradients. So classic gravity current theory from Benjamin in 1968, and then lots of experiments motivating this as well, is that a gravity current will travel at a constant dimensionless head velocity known as the Froude number. So most models impose this as a condition. So we say the velocity at the head, un, is a constant called the Froude number times the square root of the depth. Yeah, so we're also going to explore this problem with boundary conditions and initial conditions reflecting the experimental model with a box, 2 boxes of unit size. Okay, so you can transform these equations into a Riemann invariant form if you use a substitution C equals the square root of H. This splits them into 2 families of curves known as characteristics. So we have alpha, which is u plus 2c, being conserved on all curves in xt space which have gradient u plus c, and the same beta is u minus c, which is conserved on curves that have gradient u minus c. So using this method, if we can work out the values of alpha and beta anywhere in space, so where we have 2 of these lines crossing, you can work out the value of u and h. Now this method can be used to solve the dam break problem, so rather than have a finite amount of fluid, just an infinite amount of fluid behind the lock gate. That can be solved exactly. You can integrate the full system for a single release problem, but you still need a bit of numerical work to solve the equations in certain regions. And probably what's really important for sort of what I'm going to present today is that there are a few key characteristic curves which sort of partition the region of the solution into different parts where it behaves qualitatively differently. Okay, so at t equals 0, all the characteristics have either alpha equals 2 or beta equals minus 2 because they're coming from unperturbed fluid. So with the Froude number condition, we have another set of beta characteristics which have a constant and come out the back of the head here. So these characteristics here are constant, but well, they have beta constant, but of a different gradient than the beta equals minus 2 here. This region is connected with an expansion fan regime, and yeah, so the orange line is this last characteristic which has beta equals minus 2, and it represents a backwards travelling disturbance. So shortly after release you might see a profile like this, and there's that orange dot which is the first bit of the flow that's been affected by the release. Sorry, the furthest bit back that's been affected. So this reflects off the back wall at t equals 1 for a dimensionless case, and then travels back towards the head of the flow, and this now represents the last characteristic on which alpha equals 2, because all alpha characteristics from the boundary conditions there and the initial conditions there have alpha equals 2. But at t equals 1, it's the first point where the depth is not 1 at the back of the lockbox. This travels through towards the front of the flow, and when it reaches the front, this will be the first time that the head has been affected by this sort of the finite supply of material. And then the head speed will also start decreasing in time from there. So, yeah, so really, these two lines split the domain into three distinct regions. We have complex regions where both alpha and beta are varying, simple regions where one of alpha and beta is varying, and uniform where they're both constant. And where they're both constant, we have both the depth and the velocity constant as well. So the question would be is how does it extend to the double release case? So again, when we release the second lockbox, we're going to get another backwards travelling disturbance. We're going to colour this green. And we're going to get a shock as well because there's a discontinuity in the depth. I'm going to colour this as the blue dotted line. And there's really sort of simply two cases we can consider here. One which is like this, and one where this reflection reaches the shock before the shock reaches the head. I'm going to distinguish these two cases by N for not affected by the finite length of the domain and F for affected. Yeah, we can also partition our solutions depending on the region that they start in. So here's two examples. We call these C1 shocks because they're starting in the complex 1 region. And these are uniform or U2 shocks because they're starting in this U2 region. And they'll have different qualitative behavior as they travel through towards the front of the flow. So we solve these shallow water equations using a finite difference scheme and then compare we then post-process and produce the characteristics to determine what case we're in. So here's a quick example. We'll see the orange dot is the backwards travelling disturbance, which reflects back and forward. The shock's release, which is the blue dot, and the green dot is the backwards travelling disturbance. And in this case, the shock has reached the front before that backwards travelling disturbance is caught up. So now here's two different cases where one of them is going to be affected by the finite length of the domain. So we'll see the one on the left will be similar to before, whereas the one on the right, the green dot, should reach the blue dot before the blue dot reaches the front. Yeah. See, there we go there. And we're going to label the time that the shock intersects with the other three lines by a triangle, a diamond, and then a circle for the green line. So you might ask, well, what does any of this mean? Does it make any actual difference? Well, it does. So for this case, where we are affected by the finite length of the domain, we can see that pretty much as soon as that characteristic reaches the back of the shock, our shock speed starts decreasing. And this has been observed for pretty much all the cases we did. So we did a sweep of the parameter space. We found this is the boundary between these should be Fs here, not Ns. But sort of in this region of the parameter space, which is Froude number against the release time, we have all of these shocks slow down once that backwards travelling reflection reaches the shock. And in all these cases, it doesn't. There's also distinctions between these as well, but I don't really have time to show them. Okay, I'll leave the conclusions up. Thank you.
Okay, so we have time for some questions. Yes?
It looks to me like the whole problem sort of looks like the shock tube problem for like supersonic flow.
Yeah, so
Is there an analogy?
yeah, so this definitely is for modelling gravity currents with just a single lock release. There is a strong connection between like supersonic flows, like piston flows and things like that. And that's how a lot of the theory in studying like shocks in shallow water has come from the connection between those two fields.
Question? Thank you very much again. Thank you.
Thank you. Hi, yeah, so I'm going to talk to you about a case study I've been doing on Typhoon Haiyan and Typhoon Hagupit. And in particular, I'm going to be looking at the predictability of these storms. So tropical cyclones, what are they and why do we care? Well, they're massive storms and they're capable of causing a huge amount of impact on regions where they make landfall. So this image at the bottom right, this is the aftermath of Typhoon Haiyan, which is one of the storms I'm looking at. And you can see that the strong winds, the flooding due to the extreme rainfall and the storm surges has completely ruined the country. And in fact, it caused over 7,000 deaths and $1.8 billion of damage. So clearly it's really important that we accurately predict where these storms are going to go and also how intense they will be. So I mentioned that I was looking at the predictability of Haiyan and Hagupit and comparing these two storms. So in this slide I'm going to try and motivate why and explain what I mean by predictability. So here we have two track forecasts, so where the storm's going to go, and they're just one single forecast. And whilst they give one scenario of what might happen, they don't really tell us how much confidence we can have in this prediction. So the atmosphere is a chaotic system, so a small error in initial conditions could amplify and drastically change the forecast. And that's why we use ensemble forecasts. So this is a method we perturb the initial conditions, we perturb the model physics, and we get a whole range of different forecasts, and from there we can analyse how much confidence we have in our forecast. So at the top with Haiyan, we can see that already we can have quite a good amount of confidence that the storm's going to actually go across the Philippines and this region. If we compare this to Hagupit, well, the storm, a lot of the ensemble members predicted that the storm would recurve to the north, so completely missing the Philippines altogether, whilst other ones went across. So this is what we mean by predictability. Haiyan is quite predictable compared to Hagupit, where it was a lot less confidence in our forecast. And just to add on what actually happened, to show point, so Haiyan, the best track line, which is a black line, that did actually stay within the ensemble spread, and Hagupit was also in the ensemble spread, but the forecasts were less useful. So I really want to compare these two storms and explain why was Hagupit so unpredictable. To do this, I'm using the Met Office's unified model. I'm running ensemble forecasts both globally, and the results you just saw are from the global ensembles, and also using a convection permitting regional model, which is higher resolution and also means you can solve convection explicitly rather than parameterize it. So if I jump straight into the track forecasts, well, two at the top I've just shown you, but if we look at the ones at the bottom, these are the convection permitting forecasts. For Haiyan, at first glance, you would say, yeah, it's the same as the global forecast. The spread's quite small, and they surround the best track line quite well. More further inspection, you see that the time actually lags behind the global forecast. But for this talk, that's not too important, and we don't mind too much. For Hagupit, well, something interesting is going on in the convection permitting model and the global model. So this region where the tracks begin to diverge also corresponds to, in the convection permitting, where there's a systematic turn to the south from all the track forecasts away from this best track line. So clearly, at this point in space and time, something interesting is happening with the storm that's causing the spread in the tracks. That's what we want to investigate. So to first approximation, we can say that tropical cyclones tend to move with the environmental flow. So we can take a deep average layer of the atmosphere between 850 to 200 hectopascals, and we can plot the streamlines, and this is really showing where the wind's going, what's driving the storm motion. So first we'll look at Haiyan, and I've taken a global ensemble average. This is because the same features were shown in every ensemble member, so there's not much to see when you look at different ensemble members and try and find the differences. And Haiyan was a pretty textbook storm for this region. It formed on the southern periphery of this subtropical high, and this is anticyclonic, so it's going clockwise, the winds around the high pressure system. And it just follows the southern periphery of this high across the Philippines and in a straight line. If you compare this to Hagupit, well, Hagupit forms on the southwest periphery of this same subtropical high, but it ends up in a region where there's a high pressure system to the east and also to the west. So this is sort of like a saddle point in the environmental flow. So you can think this high pressure system wants to drag the storm to the north, make it recurve away from the Philippines, compared to the east, where the high pressure system is trying to drive the storm across the Philippines. And this is what we've seen in our original ensemble forecasts. So it suggests that if you change the position of the storm relative to the high pressure systems, you're going to get a different track forecast. It's going to be very sensitive to the storm. And that's what we wanted to investigate. So to do that, we wanted to find an environmental wind which describes the motion of the storm well. So to do that, we use a technique by Galano and Davis, where we try to remove the vortex. That's the tropical cyclone vortex. To do this, we use the vorticity and divergence associated with tropical cyclone to calculate the stream function and velocity potential using Poisson solver. And from these, we can get the non-divergent and irrotational winds associated with the storm. So then if we take our original overall wind field, subtract the non-divergent and irrotational winds, we're left with what we call the environmental winds. So graphically, we can show that. So this is just a snapshot of an ensemble member at some time, I can't remember which. But you can see before we remove the storm, we have quite a strong vortex, we have swirling winds around, and then afterwards we're left with this, well, vorticity's almost completely gone apart from a bit of remains here. And there's this easterly flow which just goes straight through where the storm was. And that corresponds to the direction that the storm was actually moving in. And we've tested it by looking at motion vectors of the storm compared to environmental winds, and this environmental wind field does accurately predict where the storm was going. It matches to the storm's movement. So now that we have this environmental wind, we want to look at the sensitivity of the storm's position to its future track. So to do this, we've used trajectories just in the environmental wind field. So this magenta dot is where the storm was forecast to be 24 hours into the forecast. And we've used our environmental winds to start trajectories in a 2 by 2 degree box around where the storm was. And then we want to see whether, so in this just one single ensemble member, we want to see whether the trajectories spread out like we saw in the track forecast, or whether they stay together. So if they spread out, we can say, well, it's sensitive to the position of the storm, where the trajectories, well, the future track of the trajectories is sensitive to the original position, whereas if they stay together, we can say, well, in this ensemble member, the storm was always going to track this way, and then in a different ensemble member, there must be something different about the environment. So if we see what happens, on the left we have our global forecast, and on the right we have our convection permitting. And straight away you can see the global forecast shows the same characteristics as our original full ensemble. And some trajectories recurve to the north, and some go straight towards the Philippines. And in our convection permitting, you can sort of see the same southern turn, southward turn away from the best track line, especially in trajectories which were initialized to the bottom of the box. So this sort of shows that the uncertainty in Hagupit was due to environment it was embedded in. One small change in position could drastically alter the future track. So just to show that point more, to compare it to Haiyan's track line, so we do exactly the same technique. I've just shown the global here, but convection permitting is exactly the same. We start our trajectories in the box, and there's very little separation, and they're all very predictable around the best track line. So just to summarise, both storms showed a lot of similarities in the intensity of and the track, and we both made landfall over the Philippines. But the spread of the tracks was much greater for Hagupit than it was for Haiyan. And essentially, by looking at the environmental winds and using trajectories, we have shown that the uncertainty in track forecasts for Hagupit is due to environment it was embedded in. So the small changes in position earlier in forecasts, which you would expect anyway, can drastically change its future track. That's it. Thank you. I'm not sure what you mean.
So I think you want some uncertainty in your forecast, but
Yeah.
you could also do a, let's say, a sensitivity analysis, so you differentiate the result at a later time with respect to the industry condition. You would also get an estimate on how your results would deviate from each other.
I'm not too sure what.
Yeah.
I'm not too sure, sorry.
This question of the spread, given the changes in the initial condition, I guess, is the question, isn't it?
We are looking at doing some more sensitivity tests where we are sort of driving, using the same initial conditions but just changing the physics, or using the same physics and just changing initial conditions, so well, not too sure.
Any further questions? Is it always a question of this saddle point? I mean, was that really the crucial thing, do you think, in giving the ensemble spread? I mean,
I think it was in this case, yes. I think the saddle point
the
was.
saddle point in the environmental flow,
Yeah.
it's always going to be trouble.
Yeah, we think
Very
that's.
predictable.
Yeah.
Okay, right. Thank you again.
Hi, I'm Caroline Marshall, and as Chris said, I'm yet another student from the CDT Fluid Dynamics at Leeds, and I'm talking about turbulence in the body of gravity currents. So the broader work of my PhD involves using a combination of particle image velocimetry, PIV, both planar and tomographic, and three-dimensional direct numerical simulation, DNS, to quantify large-scale coherent vorticity within the body of gravity currents and to look at how that turbulence scales with both the Reynolds and Schmidt numbers. So earlier on, Paul talked a bit about what a gravity current is, and he introduced lock exchange style flows. Mine are a bit different. I'm looking at constant influx. So there's a continuous pumping of fluid in rather than having a fixed volume that's suddenly released. So why is this worth our time? Interest in gravity currents generally is well established. The head has been extensively studied and its structure is pretty well understood. On the other hand, very little looks at the body, despite the fact that this can form the vast majority of the flow. Large-scale coherent structures are interesting because of their ability to transport mass, momentum, and temperature, and therefore influence flow properties in that way. And by large scale, we mean those with a size on the same order as the height of the body. Finally, why Schmidt number? I thought there might be some people here today who aren't familiar with Schmidt numbers, so for them, it's defined as the ratio of momentum and mass diffusivities, similar to a Prandtl number. And physically it compares the thicknesses of the hydrodynamic and mass transfer boundary layers. Most of the existing numerical work looking at gravity currents assumes a Schmidt number of 1. This is the kind of right ballpark for a gaseous flow, but for a solute-based flow, which many people do look at, it should really be more on the order of 1,000. We thought, therefore, it might be interesting to establish where that assumption is reasonable and where it makes a significant difference to the flow. The difficulty is that the computational cost of 3D DNS scales not only like the Reynolds number cubed, but also like the Schmidt number squared, so it rapidly becomes very expensive. So my domain looks a little bit weird. That's because we're hoping to directly compare the PIV and the DNS at the end of the day. So the PIV domain is much less flexible, so we've had to base our numerics on that. So this whole thing is airtight. We then have these two raised sections, one at either end. They're intended to capture any air that comes in through the inlet or the outlet. The inlet is a 1-inch pipe inflow with a coarse mesh in front of it to give a homogeneous turbulent inflow. And there's also this full-width horizontal piece of plastic in front of the inlet to promote horizontal spreading and to limit the initial height of the flow. The outlet is at the bottom of this big drop, which just maximizes the duration of the steady phase of the flow. For the DNS, all of these walls are no-slip. The inlet is approximated as 7 fully developed pipe flows with some artificial turbulence added in, and the outlet uses NEC 5000's outflow boundary condition. To vary the Reynolds number, we keep the influx the same and tilt the whole rig. I'm going to be showing you some plots later on, just for context. Those plots are a central slice taken from this this central section here. To give an idea of what these flows look like, This is one of my lab-based flows. It has a Reynolds number on the order of 5,000 based on the height of the body and the velocity within the body. Once the head is gone, we get about a minute's worth of this steady body. And within this section, the time average properties are constant. I'm told it's pretty boring to watch for most people other than me, so let's move on. The flow is governed by these equations that you see up at the top here. The S represents salinity, and beta the saline contraction coefficient. The values of those are chosen to give a density difference of 3%. Again, that's dictated by the experiments. We solve them using the spectral element method, NEC 5000, which was chosen because it's open source, but also because it has really good scalability and parallelizability. So what have we found so far? What you see on the left of the screen are pseudo-color plots of salinity taken from our investigations, and on the right are contours of density taken from a paper by Bonometti and Balachandar. So Bonometti and Balachandar looked at lock exchange style flows rather than constant influx, but despite that, there are some similarities that you can see here. So everything on the screen has a Reynolds number of 100, and going from top to bottom, Schmidt numbers 1, 10, and 100. As Schmidt numbers increase, you can see we get a more defined head. The dense fluid gets much closer to the front of the flow. There's also a thinning of the mixed layer. And looking at the constant influx currents, so ours on the left, you can see the velocity is slightly increased. So this is all from the same time step. If we increase the Reynolds number a little bit to 500 and look at Schmidt numbers of 1 at the top and 10 at the bottom, we see some of those same features again when we increase the Schmidt number. The denser fluid gets closer to the front, you get more structure forming, a more defined head, and in fact more structures forming in and around the head. The difference in velocity is also slightly more pronounced as we increase the Reynolds number. So as I mentioned, we're interested in identifying structures within the body of the flow. So a huge number of different techniques exist to identify these kinds of structures. They all have strengths and weaknesses, so we thought the best thing to do was use a few and compare them to see where they overlap. So the first that I'm going to talk about today is conceptually the simplest. We can look at fluctuations. So because the flow within the body is pseudo-steady, so we've got those time-averaged constant properties, we can look at fluctuations in downstream velocity, so pseudo-color of downstream velocity fluctuations, overlaid with streamlines of downstream and vertical fluctuations to find regions of possible rotation. The second is a swirling velocity, which involves finding the eigenvalues of this Jacobian matrix J. That splits the flow up into translational component, A, and a rotational component, B. And again, we can produce pseudo-color plots of B to find possible features of interest. Finally, a residual vorticity, which is based on triple decomposition of relative motion near a point. So it splits the flow up into pure shearing, rigid body rotation, and irrotational straining motions. So we can then remove the effect of shear to be left with a residual vorticity, which hopefully just looks at the things that we're interested in. If we apply those techniques to the results that we have, so this is for Reynolds number 500, Schmidt number 1 on the left and 10 on the right. We can see that as we increase the Schmidt number, the number of structures within the body is reduced. They actually get a bit bigger and a bit weaker as well. So we can see using the other two techniques that there's quite a bit of overlap between what we're seeing. So the white line here is the height of the velocity maximum within the flow. Yeah, it is quite reassuring to see that we are getting structures in similar places, whichever technique that we use, or not, as the case may be. And because it's always nice to finish with a pretty video, this is actually for the Reynolds number 1000 Schmidt number 1 case. It was just the nicest to look at. We can see how those different techniques vary over time, which is quite nice. is about 16 seconds worth of flow. So just to finish off, we've used NEC 5000 to investigate the impact of Schmidt number on constant influx gravity current flow. In particular, what we found is that for at least low Reynolds number cases, it has a significant effect. An increasing Schmidt number seems to result in a slightly higher speed of propagation, the denser fluid getting closer to the front of the flow, more structure in and around the head, and fewer and larger structures within the body. Thank you very much.
Questions for Caroline?
At the end you showed a higher Reynolds number simulation. Were you able to increase the Schmidt number as well, or is it becoming too expensive for that?
So the cases that we're hoping to look at are here. So on the ARC facility that we have at Leeds, I've managed to do the Reynolds number 100, 110 and 100, 500, 1 and 10, and 1000 Schmidt number 1 cases. We can maybe do a few more, but yeah, we are hoping to look at a wider range using a facility over in Illinois. So hopefully we'll have some more.
Any other questions? Yes, over there.
Do you have any statistical measures for the engineering structures to have a quantitative comparison?
Not yet. It's on the to-do list.
Okay, thank you very much. Okay, thank you very much.
Thank you very much. So the first thing I have to say is that, again, this is a slight break from geophysics, but here we go. It says viscoplasticity. I'm afraid I'm only going to talk about rate-independent models today, and in the context of stability and instability of simple shear. So I want to consider a class of plasticity models for the flow of granular materials. Such models are widely used in geotechnical, civil engineering, and indeed also in geophysics, so I hope there is some relevance of what I'm about to say to people here. And as it says again, I want to consider the stability and instability of planar solutions, simple solutions in which the velocities are linear in the spatial variables and the stresses are constant. I would like to draw some conclusions concerning the flow of granular materials, but just to skip to the end, what I really want to do is to emphasize the role of mean grain spin, and this is a quantity which is completely missed out in standard continuum mechanics. I need to develop some notation, so here it is. X's are just spatial coordinates. D0 will denote time. Classical quantities, i.e. an ordinary continuum quantity, will have V for the velocity vector, sigma for the Cauchy stress. And then I'm going to introduce some Kossora quantities. Mu will be the couple stress, and omega will be, capital omega will be the intrinsic spin vector, as it's called in Kossora theory. I'm interpreting that as the mean grain spin. It's convenient to transform the stress variables to these invariant forms. So P is the in-plane pressure, Q is the maximum shear stress, the skew symmetric stress is given by R. These are all invariants. The absolutely crucial quantity for this theory really is this rather mouthful to say, this psi sigma. And so it's the angle that the greater principal stress makes with the of the symmetric part of the stress makes with the x1 axis. And so if we then change everything to these variables and also use the Coulomb yield criterion, any criterion could be used. I would prefer it to sort of maintain hyperbolicity of the equations, but other yield conditions could be used. But this is my favorite. I do think it's the best model, the best yield criterion for granular materials. So if we plug all that information into the two equations of motion, we'll get some equations that look like that. We're going to assume incompressibility. We want simple shear, which is an isochoric flow. So we'll have incompressibility, and then we need one extra kinematic equation. And this depends, okay? We're talking classically again. Either we use the plastic potential model, and this equation really says that the strain rate and the stress share the same principal directions. Or we could use, say, the double shearing model, which, if you look at the first two lines of those equations, they're the same. So this latter one is not those quantities are not coaxial. There is this forcing term. And this term, whoops, I didn't mean to do that. I meant to do something else. I meant to, use the pointer. So there is a forcing term, if you like, which renders this thing non-coaxial. And really, this is the vorticity minus the stress rate term that we have here. Okay, so if we then look at a simple velocity field, simple shear, this determines the value of psi sigma in these two models. So the plastic potential solution would give us psi is pi over 4. The double shearing would give us psi is pi over 4 plus phi over 2. And so if we imagine we've then prescribed the pressure, then of course we can read off the value of Q from the yield condition. Want to consider the instability of such flows. And so big letters denote the underlying solution. Prime quantities denote the perturbation. And so the total solution, if you like, is the sum of those two things. And we want to do the usual thing, substitute into the equations, throw away all nonlinear terms in the prime quantities. The uppercase variables solve the equations, and so it enables us then to consider a perturbation of those linear equations, and we convert it then to an algebraic problem. Derivatives go to those algebraic quantities, and we will end up with a system of equations that looks something like that. I'm not going to write down what the capital A's and little b's are because they're rather complicated and I don't have time. We will get, if you like, we will get non-trivial magnitudes of the perturbations if the determinant is 0. And this thing here, this definition, is of crucial importance. The really important quantity is a tan 2 psi k. So I'm going to call k the magnitude of the frequency of the perturbation, and the psi k is going to be the phase or the direction of the perturbation. We have these definitions. This is the key quantity, this tan 2 psi k. If we do that, the big Q's are the second invariants, really, of the stress and the strain rate. We get the result of our stability analysis is something like this. And we can see that these blue terms here take both positive and negative values. There is a nice minus sign here, but these now take positive and negative values. And so the perturbed solution, one of the perturbed solution, grows exponentially in 4 wedge-shaped regions. And so you can see it's unstable. This is because, or rather, this is a consequence of the fact that this model is ill-posed. Similarly, if we do the double shearing model, we get, there's no minus sign here now. If we look at this mess is always positive. We can see that we're actually going to get one positive, one negative root. It is highly reasonable to say that the magnitude of psi sigma minus psi d is less than or equal to pi over 4, so that's not a problem. Again, but there is one positive, one negative root, and so the underlying solution is stable. And the perturbed solution now grows exponentially for all values of psi k. Psi k sort of runs minus pi over 2 to plus pi over 2 to cover the whole range. Okay, so we have two ill-posed models. The model I'm presenting today, I sometimes call the augmented potential and sometimes the double slip and double spin. Again, you can see that it's very similar to the previous models. Top line is the same, but now the forcing term, instead of having the stress rate, it now has a Kossler quantity, the omega 3. And so this is where we bring in the mean grain spin. This quantity is the mean grain spin, but I seem to be talking about classical flows so far. So classical flows correspond to, well, either if there is no external boundary, all I can say is that the omega is a constant. If I do have an external boundary, then I can actually say that omega 3 is 0 if I, at all places and times. And so what I'm trying to say is I'm modeling classical flows using an extended Kossler material, Kossler model, but I've not yet gone into the Kossler stuff. I want to just look at the classical situation. And now we see that if we do the stability of simple shear, we have a nice minus sign here. These quantities are positive, and everything is, this is squared up. This is non-zero. And so we see that we get a nice we get a nicely decaying value for the real part of I omega. Again, you know, the very reasonable condition of psi, the difference between psi sigma and psi d is d is the deformation rate or strain rate. So this is talking about the directions of the principal axes of the stress and the strain rate. Oh dear, oh Lord. Right, okay, so we're going to have to go very quickly now. So because we get a nice result, I can have some nice theorems about what's happening here, but I clearly can see I'm not going to have time to do it. So now to bring in the, if I now bring in the Kossora quantities, the simplest possible model is this. This is a rotational yield condition. This is the spin equation of motion. This is a constitutive equation, a plasticity constitutive equation. That's a plasticity multiplier. We get rather a complicated parameter E. And if we look at the real part of e to the I omega, if we put E is equal to 0, because I'm only looking at classical flows, and E is 0 for such flows, we can see that this will go to 1 minus 1, which is 0. And so we actually get that the stability has been reduced to neutral stability, which is not so good. Unfortunately, if we look a bit more carefully at this, if E is not naught, then simple shear is unstable and the equations are ill-posed. So this model is too simple. It won't do the job that we want. And so we have to go to slightly more complicated Kossora equations. And here the terms in blue are the differences between this Kossora model and the previous one. And so now it's got a symmetric Cauchy stress. R is 0, but it has a spin gradient, the d omega 3 dx1, etc. And if we now do the obtain 3 possible values, we see that the Cauchy stress effects decay nicely. The couple stress effects decay nicely. But the grain inertia effects just give neutral stability. The full Kossora model, which is the one that we have here, I did think I would leave as a calculation for any interested listener. So I'll go straight to conclusions and say that simple shear is unstable in classical models. It's asymptotically stable in the DSDS model, which means that we can use it for classical problems and get nice, stable solutions. The first kind of Kossora model I chose, I had neutral stability. The second one, we had, again, neutral stability. And in the third one, I haven't yet completed the calculations. It looks as though I have to stop.
Okay, thank you very much. We'll have time for a quick question. If anyone has a question. Yes?
I mean, you've got the spin going on. You've got the spin going on.
Yes.
But don't they frustrate themselves because when one wire is turning?
Yeah, absolutely. In a sense, this is a mathematical exercise. What I want, the classical models have no grain spin. And I want to go from that to a model which is including grain spin. And that, yes, that will indeed distort, disturb, somehow change the, that simple shear. I would say, would like to say that there are solutions which are simple shear, in which the magnitude of the simple shear depends upon the omega, the spin. So I had 2 simple shears there. There is a third one for this model, which contains omega. And so those, if you're thinking of the layers and so on, in terms of those original things, yeah, those solutions go away when the grains spin. And so the whole question is, when do grains spin and when do they not? And in the literature, if you see it, when people sort of get these shear bands and things, grain spin, the average, the mean grain spin is 0 outside the shear band, and there is then there is rotation within the shear band. And so that's what I'm trying to talk about here. Sometimes the ordinary solution will be okay, but then sometimes in a shear band you need to take into account these other spin-dependent solutions.
Okay, thank you very much.
Yeah, so essentially I'm going to be reporting some details from our ongoing experimental work that we're doing that is essentially looking at snowflakes, which is a bit of a wacky project, but there we go. So the reason that we're interested in this is that it's a really important problem in a meteorological context. So for instance, the fall speed of ice crystals is really important because it determines the lifetime of clouds. This in turn has a huge impact upon the Earth's atmospheric radiation budget. Now this process is represented quite prominently in climate modelling, and therefore it's a major source of uncertainty when using our climate models. But it's not just fall speed that we're interested in. So for example, the orientation of falling ice crystals is really important when we're trying to interpret radar measurements. And we can also say that as well, the aerodynamics of these ice crystals kind of governs every aspect of how they evolve as they fall. So it controls how they grow from water vapor, it controls how they may collide with water droplets or other ice crystals. Now, all of these processes are actually fairly poorly understood, and the reason for this is that it's very difficult to observe this natural process. So for instance, ice crystals are very small, they're easily blown by the wind, and they have a tendency to melt, evaporate, or break when you try and handle them. Now there is progress being made in the use of in situ instrumentation, but as yet this provides limited measurements. And whilst there is progress being made using numerical studies, this is a quite computationally expensive problem to solve, particularly when you use realistic geometries, and therefore also the data requires validation. So the approach that we're using is to essentially fabricate scaled-up models of real ice crystal shapes and then drop them in viscous liquids where we can more easily study them. So the kind of concept is that we're exploiting dynamic similarity, because when the crystals fall steadily, their aerodynamics is governed by just their geometric shape and their Reynolds number. And therefore the relationships between dimensionless quantities, such as their drag coefficient and their Reynolds number, are exactly the same as they would be in the atmosphere. Now, we're also kind of simplifying this problem a bit more by studying the simple case of crystals sedimenting in otherwise stationary fluid. And the reason that we're doing this is we're trying to really focus on the kind of geometric aspect of the particles rather than the flow too much. So some of you might have been in the talk yesterday on plankton sedimentation, and it was really raised in that talk that orientation and geometric effects are really important sedimentation problems, but we don't really understand them, and that's what this work is trying to address. So there were several studies that kind of adopted this approach with regards to snowflakes in the 1960s, but the models that they used were machined by hand, so you were very limited in the kind of shapes that you could use, so they weren't particularly realistic. And the new idea in our study is that we're using 3D printing to try and produce more realistic ice crystal shapes. So the experiments that I'm describing today are kind of a first step in towards this more systematic study. In its very early stages, we're only kind of 8 to 9 months into a project. So I'll give first an overview of kind of the experimental process. So we start off with a computational model that describes an ice crystal growth process. We then use the output of this model into open source CAD software, which we produce files that we can then 3D print. And you can see on the right an example of an image of an actual particle that we 3D printed, which typically have a scale of a couple of centimeters. Now at the bottom of the slide, you can see a range of just a small range of some of the different shapes that we've considered. So they range from very, very simple planar models, so a hexagonal plate, to much more complicated and delicate aggregate type models. And the idea underpinning all of these different shapes is they are representative of shapes that grow in the atmosphere and to different ranges of temperature and humidity. So once we've printed these models, we then drop them in an experimental tank. So we're going to be using 2 different sedimentation tanks, each of which is going to be filled with mixtures of water and glycerol. So the shorter tank is just over 1 meter tall, and the taller tank is closer to 2 meters tall. And the idea is that once we've released the particles, they should be able to reach a steady state before we start taking measurements. And we're taking measurements using a system of 3 synchronized cameras, each of which has an orthogonal view. So we've got one looking through 2 different sides of the tank and one up through the base of the tank using a mirror. And we're providing illumination from LED panels. So each camera is essentially recording a projected image of the particle, so essentially its shadow. What we end up with are 3 videos like that you can currently see playing on the slide now. And the idea with our analysis is we're going to reconstruct the position of these particles in terms of both their physical position and their orientation. And we do this firstly by simply just tracking the location of the particle within each image frame, and then use a series of calibration images to reconstruct where that lies in the actual physical space. And we then reconstruct the orientation using what's essentially a trial and error type approach. So we have a digital model of the particle, and we then reconstruct synthetic images that each camera would record if the particle was orientated in a certain way, and then determine the correct particle orientation by minimizing the difference between these 2 sets of images. So it's quite computationally expensive, but what we end up with is data that looks a little bit like this. So we can see particles that rotate as they fall, and we have a complete description of its movement. And using this kind of data, we can investigate characteristic features like its Reynolds number, its drag coefficient, and any kind of periodic or oscillating motions that it goes through. So in terms of results, as I indicated earlier, we're at quite an early stage, so I don't have a nice complete data set that I can show you, unfortunately. So what I'll try and do is just give you a kind of a flavour of the things that we're looking at and where we're hoping to go with the study. And the first thing that I'll talk about is the preferred orientation that these crystals exhibit when they fall with a steady fall. So there are various assumptions about this in the literature. So some people assume that ice crystals fall with a completely random orientation. Some people assume that they will fall so that the maximum span lies in a horizontal plane. Others will assume that simple symmetrical ice crystals have a preferred orientation, and others, like aggregates, just completely tumble. What we actually find with our experiments is that of all the shapes that we've tried, they all have a clear preferred orientation over at least some Reynolds number range of order about 100. And you can see some examples here for just some of the different shapes. Now, as a very, very rough rule of thumb, we find that they typically try and arrange themselves to be as long as possible in a horizontal plane, but the detailed answer is more complicated than this. So, for example, when we look at different arrangements of rosettes, which are the two shapes that I've highlighted, we find that that's not the case. And we don't really know why yet. We're still looking into that. What you find as well is when the Reynolds number increases, you start to see unsteady secondary motions. So the videos that are playing now are of two crystals both falling with a Reynolds number of approximately 280, where we've used dye to visualize the wake, which you may or may not be able to see on the right. And as you can see, that as before, so this branch crystal on the left falls quite steadily, it has a steady wake, but the solid crystal on the right undergoes this periodic swing glide type motion, which is associated with vortex shedding, and you get these different types of motions depending upon the geometric shape and the Reynolds number. What's really interesting actually is that some of these aggregate particles, which have a really regular geometry, are some of the most stable shapes that we've studied so far. So they can have a stable configuration even at Reynolds number of order 1,000. And what's interesting is they often rotate within the plane, but they don't appear to oscillate at all. But we still don't really understand what controls this yet, and we're going to be doing more work to look into that, potentially looking at things like the inertia tensor of particles. Now, the final results that I wanted to talk about was looking at the actual fall speed of these crystals. So in a meteorological context, there's two widely used approaches to do this. The first is very, very simple, which is you just take a power law that relates the terminal velocity of an ice crystal to its maximum dimension. And as you might imagine, there is a number of issues with this approach. The first of which is there's no account for the ice crystal geometry. So what you find is that you have to have a very, very large ensemble of different power laws, each of which you can apply in very specific atmospheric conditions. And the second is that when you actually look at the data, there's an awful lot of scatter around the average fits. But despite these issues, they remain very popular because they're just so simple and easy to use. But the other approach that we're going to kind of be arguing towards in our work is a standard kind of drag coefficient approach. So the most common parameterization in this context is a parameterization proposed by Mitchell in 1996, which assumes a universal drag curve, or drag Reynolds number curve, of this kind of form here. And this was proposed initially by analogy to previous work looking at spheres, but uses slightly different coefficients, but still doesn't really try and do any explicit account for the shape of the particle. So what you find when you look at experimental data is, on average, it actually underpredicts the drag coefficient, so it overpredicts terminal velocity. And as you might expect, there's also a geometry effect. So when you look at it more closely, we find that crystals that have what are dubbed an open geometry, so they tend to be things that are branched, there's an even worse agreement for these kind of geometries. So what we're going to hopefully try and do is try and evaluate more versatile fall speed parameterizations that use shape parameters to try and account for some of these effects. Now, looking forwards, the kind of the kinematic approach that I've described so far is obviously only really half the story. So we have the drag and the orientation potentially, but we get very little insight into the actual flow. So what we're going to be doing is complementary PRV experiments to try and derive some insight into that dynamics. We're also going to be doing experiments in air. So far the analysis that I've described kind of relies on the flow being steady. So then it's governed by just the Reynolds number and the geometric shape. When the flow is unsteady, the density difference becomes important. So that's not matched in our tank experiments as to the actual atmospheric problem. So that's why we're going to be looking at real ice crystals as well, or crystals of life size in air as well. So as I'm out of time, I'll leave it there. But thank you for listening.
Time for a few questions.
So it depends on what Reynolds number you're talking about, essentially. So, Reynolds number is below 1. What you tend to find is the planar ones fall with whatever orientation they start with. For the Reynolds number between about 1 and order 100, depends on the exact shape, they fall so that the maximum area is exposed to the flow. And then as the order goes beyond 100, you start seeing these periodic and oscillating motions. So it depends upon the regime that you're talking about. So for instance, in the talk about plankton yesterday, perhaps it's less of an issue because it's even lower Reynolds number where there perhaps isn't this orientation effect.
Yeah, I was wondering if you looked at whether there's effectively a hydrodynamic radius you can define. You have that sort of result for spheres.
Yeah.
So at low Reynolds number, the hydrodynamic radius tends to be the largest dimension, but I wondered if with these intermediate ones, whether there's the same kind of intermediate length scale you can identify that would collapse the data.
I mean, at the moment, we've not done too much in terms of fitting because we don't have that much data. What I would say is length scales in this meteorological context are fairly poorly defined. So what they've used so far is just the maximum dimension, because if you look at real ice crystal, that's relatively easy to measure, whereas other more complicated measures aren't. So one thing that we will be looking at is kind of other measures of this characteristic length scale to see where they collapse data a bit better. So that's hopefully where we're going to be going towards it.
Well, thank you very much.